Hello, everybody. We'll wait a few minutes for others to join. With luck, what you're looking at now tells you that you're in the right place. Okay, while people are joining, could I get a volunteer or two to head over to HedgeDoc and try to take some brief notes on the discussion? Okay, still looking for a volunteer or two to take notes. Otherwise, you're stuck with me taking very, very brief notes. Um, just need over in the hedge talk for the session. Just make an occasional note of what's going on in the discussion. That would really help. And I think we'll go ahead and get started. I need to show. Where is it? Come on. This. Whoops. Permission denied? That's not right. Hang on. Okay. All right. There we go. That took a few more clicks than I was expecting. This is the Note Well slide. This is an IETF meeting. So the contents of this slide apply. You're expected to be familiar with it. Okay. Let me see if we can go. Nope, that's not what I wanted to do. We will try it this way. One of these days I will learn my way around Meet Echo. That's what I wanted. Okay, so we're right in the middle of the quick intro and agenda bashing, and unfortunately, I need to bash the agenda. We're going to try to do items 1 and 2 in about 45 minutes each. I have a conflict at 9:30, and unfortunately, neither of the DetNet chairs are able to attend. So we're only going to have about an hour and a half this morning. And uh, I will leave the meeting open. It might run till 10 o'clock, but I'm not sure whether that's going to work. Okay. Any comments, questions? Anybody else want to try to bash the agenda? Okay. Process-oriented topics. So we have in the proceedings of the last couple of interim meetings some evaluation slides that take a look at the um, the TSN mechanisms. Um, what I'm planning to do for the meeting next week is basically grab those slides, put a few text slides in front of them to indicate what we've been doing in the interim meetings, and that's what'll go into the the main meeting presentation. I mean, if anybody has a evaluation slide of one of the proposals, and this we could do a little bit of discussion of that now, but I don't think we're going to start doing serious evaluations of the proposals until after the IETF meetings next week. Okay, Turles.
No new slides on that side. I was too busy with what I'm presenting today and other stuff. I think the main point that I think I raised already was that I don't think in the evaluations, and maybe therefore in the in our requirements document, the problem of jitter is not given high level enough importance, right? So I think that should be a separate line item, a separate point in the evaluations, and so that we can independently of latency evaluate that. So that I think is my main concern. Thanks.
I would suggest you send an email to the list because that needs to be reflected in the requirements draft. In essence, we're going to do the technical evaluation primarily against the contents of requirements draft. So if you think the requirements draft doesn't have enough discussion or requirements around jitter, please send a note to the list indicating what you think needs to be changed and where in the requirements draft it might go.
It in there. It's just too much hidden. I sent that to the co-authors, but I don't think one
No,
of us
please.
has that point yet. I will. I will.
Yeah,
Thanks.
sending the co-author is a good start, but please send it. Please send it to the list because ultimately that is a working group document, and the contents of it uh, are whatever are subject to the consensus of the working group. All right. Do any of the authors of the proposals want to be brave and put up an evaluation slide for their proposal and see what we think of it? Shafu?
Hi, David. Uh, 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 do you see that if we have prepared a slide for the proposal, for example, the line and the TGF and or TCGF?
If you have such a slide, we could take a look at it now. We will want such slides on all the proposals at some point after the IETF meetings next week. Do you have such a?
I'm sorry, I have not prepared it.
Okay.
I've just give a table and a draft.
Okay. I mean, this wasn't a requirement for this meeting. This is an opportunity. If somebody has such a slide, we'll be happy to look at it. It'll be a requirement for proposals that we consider at some point after the meetings next week. But it's not a requirement now.
Okay.
All right. Does anybody have anything else they'd like to discuss under item 1 on the screen? Xiaofu?
David, do you think that if we have time to discuss the TSN mechanism, the evaluation of the TSN mechanism, because they have a last item that is ATS solution. We have not discussed the last time.
Okay. If you want to if you have the ATS slide, would like to put it up, that would be a good thing to do for maybe 10 or 15 minutes.
Sorry, I have sent the slides to you, and the TSN is just included in the
Okay.
slide.
Okay. Give me a minute or two because I have them. They're just in one of these directories and I have to remember where I put it. So okay, so we're looking at ATS. All right. Okay, let's see if this works. This is the slide you wanted, right?
Yes.
Okay.
Yes, okay. We can get the discussion from the first item. Okay, we look at the first item, that is the tolerate the time asynchronously. For ATS, it basically reshaper, but it is optimized reshaper compared to the traditional shaper per flow. It just maintain the solo shape instance per incoming port plus the traffic class. So for the receiving function, it is not dependent on the time synchronization. So the first item, the evaluation is yes.
Okay. Does
Okay.
ATS have a
For this item,
does ATS have a problem with clock drift? And I'm guessing all.
Do you mean frequency?
I'm sorry, ask that again, please.
Okay. Do you mean the frequency synchronization for ATS?
Yes.
I think it may be yes, because even for the receiving function, it just to check in some measurement interval, the permitted traffic is allowed.
Yeah.
So
Oh.
that is still a measurement. So that is related with time.
Yeah, I don't think that's a problem. I mean, in essence, this is the primary requirement here was tolerate a lack of clock synchronization. As long as the time bases at each node are high quality, they should be a very small amount of frequency drift or mismatch. Okay, go ahead.
Oh.
Okay.
I mean, so I think
Taurus, do you have any other?
No, I think that I think the answer is it does allow clock drift, right? And I think that's actually the good distinguishing aspect.
Mm-hmm.
So what's the most accurate? So let me just take a note down that we maybe in the requirement document see. Let's check in the requirement document whether we have the most accurate way to describe it there.
Yeah, that would be good. I mean, I would guess that with high quality time sources, the degree of frequency mismatch will be small enough as to be negligible. But this really, I agree, Torles. Thank you for taking the note that the requirements draft ought to cover this. I mean, if the clocks are way out of frequency match, if they're off by 25%, weird things are going to happen.
Yeah, but that's David. That isn't exactly not the real point, right? The real point is that the requirements that are synchronous, the clocks cannot arbitrarily drift between each other. For those, we have the so-called MTIE, maximum time interval error, right? So the clocks of those can never drift more than whatever apart, right? Some millisecond, some microsecond, whatever the factor for the mechanism is. Right. So, for example, in TCQF, we said we can be a factor of 100 higher in MTIE than with CQF from TSN. Right. So we do require much less clock synchronization, but we still need it. Whereas in ATS, they can arbitrarily drift slowly over time. Right.
Yeah.
So that doesn't matter at all.
Agree. And what I'm saying here is that the notion of what you said can drift slowly over time, that topic needs to be captured in the requirements draft.
Yeah.
Okay. Janu?
If I may, I think the flow regulation function in ATS requires a clock. And if the clock drifts a lot, as David has mentioned, then it becomes a problem because each node cannot exactly regulate as it is specified. That causes the network instability. There is a paper dealing with such a problem. The one of the author was the Libotek, who actually proved that ATS has nice bound. Thank you.
But is the flow regulation something we should consider to be part of core ATS, or isn't that rather an ingress function when admitting the flow into the network? A separate one.
Oh, yeah. As you know, the ATS regulating function is required to be reside in every node.
Oh, you mean that part? Okay.
Yeah, interleaved regulator. Yeah, that regulator also needs a rather stable clock. Thank you.
Okay, I don't think that contradicts what I was saying, right? So if they are much, if the clock frequencies of these clocks are too much off from each other, then that simply impacts the calculation of how much traffic you can achieve the same latency for. So in my understanding, we can have arbitrarily drifting clocks, except that at that point in time, you need to take the impact into account, right? We did have from Mohammed and John Eves the first version of one of those, possible calculus to calculate the impact of clock drift, and I don't think we at that point in time we were far enough advanced in our thinking to accept that into the working group, because I don't think most people understood it. So I think it's possible. It's not good, but I think it's a separate aspect from clock synchronization.
Yes. All right.
I think that time synchronization is one thing, and the clock drift or frequency synchronization is another. So it is a good idea to specify exactly in the requirement document about the clock drift or frequency synchronization as well. Yeah, in that aspect, I agree with you.
Okay, so it sounds like the requirements draft may need some attention on clock drift, and as well as what Trillos mentioned earlier about better treatment of jitter. Okay, Xiaofu, that was interesting first line. Let's try the second line.
Okay. So for the second item, support the large link propagation delay. The evaluation is yes. Just like the traditional regulation function, ATS doesn't affect it's not affected by the link propagation delay. I think that has noted. If there are any comments for this item. So for the next item, accommodate the higher link speed. The evaluation is also yes, but there may need more buffer space to serve more service flows.
Zhinu, you have a comment?
Yes. It is related to 3.4, large number of flows. As you mentioned, that it has to maintain flow state. If there are too many flows, and the link speed is very high, then it certainly affects the scalability, I think. In higher speed link, we only have a very limited time to look up the flow table. So I think ATS is not very free from the high speed link related scalability. That's my point.
I think you're right, although it sounds like it's a concern that matches up well with the partial on the next line, which is that the more state you have to maintain, the harder it is to get to a large number of flows. I agree with you that higher link speed just makes it worse, but I think it's mostly about scaling to large numbers of flows.
David, process order question. Is anybody sharing the slide? I don't see it. Or
it's being shared. I see it in Meet
sorry.
Echo.
Mistake on my side. Sorry. technically, the main issue of the flow interleavers in ATS is the line rate read. No, not the line rate, but even the packet processing speed read-write cycle of the interleaver variables. You don't only need to retrieve it, but you need to write it in a speed that for the fastest possible next packet, you already are reading again the updated data. So that is the high-speed problem, right? So in our investigation back when we started TCQF, it was kind of, you can't build that at the speed and cost of what you need to do in wide area networks. So this is the read-write cycle in the hardware.
Okay, and that would be directly related to link speed, because it sounds like it doesn't really depend on number of flows.
Right. Of course, everything becomes more expensive with the number of flows as well, right? So basically, if you look at the cost of high-speed RAM that you need to do, the large, because there is some amount that you may be able to put into the network processing engine itself, which may be done, for example, with these link interface counters, right? That you have. But then if you go to a number of flows that you would need, kind of which exceeds thousands or so, then you need to look at the next level of cost, right? Everything is possible, it's just not affordable.
If I may, I
Yes,
think
go ahead.
thank you. Yeah, as David has mentioned, that the main concern here, main concern I have made here is related to number of flows. But even the flow numbers are limited. Even if the flow numbers is limited, the link speed is very high, like 100 gigabps or more. Then we only have very limited clock numbers to look up the flow table. So I'm not sure. Nobody would be free from the limitation of the high-speed link. If the link speed goes up above 100 gigabps, then yeah, every candidate can have problem. Thank you.
Yeah, I was having similar thoughts, which is that at higher link speeds, obviously your time to process each packet is reduced by the link speed. So that's going to affect all of the proposals. And I think the evaluation should be focused on proposals that fare less well because they have to do more processing per packet. Than others that perhaps have to do less processing per packet, and that might be what is useful in evaluation. Because a statement that as link speed gets faster, you have less time per packet, yeah, that's kind of obvious.
Well, David, there is a difference between the amount of processing that you're doing on the packet itself and processing that you need to do on cross-packet state.
And that's why I said per packet processing as opposed to processing each packet. So I think I'm in agreement with you. Okay, Xiaofu, let's try the next line. Xiaofu, are you still with us? There he is.
Sorry, I just not unmute and talk some words. So I agree with the discussion about for the higher link speed, we just need more description about the evaluation of this item. So for the next item is the large number of flows Okay, this item is concerned by Genu. Yes, the evaluation is partial. Oh, yes, the important concern is that the mainly the per flow states. The but the regulators index is just per incoming port plus traffic class. There may have some other considerations for this item. Okay. If there are any comments for this item, we have just discussed it. So the next one is higher utilization. The evaluation is yes. The main way upon is that we can achieve higher bandwidth utilization. My opinion is that, as I just mentioned, that ATS is a regular function. However, the higher utilization is just to see that if there are multiple traffic classes, for example, the best afford traffic can use the free bandwidth that have not actually used by the higher traffic class. So I think that is not related with the regulation function. So the evaluation is yes. Is there any comments for this item?
Genu, go ahead.
Genu?
Yeah, the regulators do not serve packets in work conserving manner. So in terms of the average delay, yeah, there is some cost for sure. But in terms of the maximum delay or the worst delay, it is proven that the IR, head of line blocking, does not impact the worst latency itself. So when you say cost about the average sense, then the statement is true. But in terms of the deterministic networking service, and I think the interleaf regulator does not have any problem here. So if I were you, I would say for 3.5, the ATS meets the requirements. Yes, that would be my answer. Thank you.
Carlos, did you want? No, okay.
So Genu, I'm not sure how I understand. Do you see for the next item 3.5 prevent the flow fluctuation from disrupting service? The regulation function has some affection for this item.
Yeah, I was talking about the nodes for the item 3.5. Yeah,
Okay.
but as I see it now, I think the nodes here and the requirements itself is not very well related in some sense. Is that what you are saying, Xiaofu?
Okay. So we go ahead for the 3.5. Now, if we look at the evaluation result, that is say the problem of IR method of line blocking should be considered. So I just hear your opinion that is not affected the worst case delay. Yes, I agree with this point. I just wanted to see if there have any proof that, for example, some paper describe this problem is not actually existed. Okay. So we have just discussed the 3.5. The evaluation is partial. So the main reason is that the state is cost that is need to maintain the IR per hop. If there is not any other comments, so we go to the next item. The next item, let's see, that is be scalable to a large number of hops with topology. This we need to consider flow aggregation strategies at the transit nodes, and end-to-end delay upper bound provided by ATS is large. It's basically inversely proportional to the reserved band width.
Yeah, this sounds like it's related to 3.4.1 because it's the number of flows for which one has to maintain state appears to be a factor here as well.
Yes.
Okay. Any additional comments?
I just realized that made a mistake.
Okay, where?
For 3.7, I think I'm not sure. Just realized that maybe I have mistaken that the end-to-end delay upper bound is mainly determined by the queuing subsystem, maybe not provided by ATS. ATS is just a regulation function. So this evaluation just may need to update.
If you want to send me a revised slide deck with the update, I'll put it into the meeting materials for this meeting.
Okay. I will send the updated text to you.
Okay. Karsten?
Can you please put in what actually has been discussed? I mean, having a revised slide also is a good thing, but having a copy of the slide we actually looked at during this meeting would be useful.
Yes, I'll put in, I'll make a note. Let me make a note to myself.
Thank you.
Yeah, thanks. I mean, this actually was pulled from the preceding proceedings, but I'll upload them to this one as well. Okay, I will do that. And then if I get a revised slide, I'll upload the revised slide deck as well.
David, sorry, I just reconsidered this item. I remember there's actually some paper to discuss the worst case latency provided by ATS. Yes, ATS has its own the worst case latency formula. So it is basically inversely proportional to the reserved band width. Yeah, sorry. So in brief, the text provided in the 3.7 need not to be updated. I'm sorry for that.
Okay. And as I said in response to Carson, I will put these slides, which were in the last materials for the last meeting, into the materials for this meeting so people can find them.
Works for me. Thank you.
You're welcome. Thank you for reminding me to do that. Any other comments or questions? Okay. Turles, if I can get your slides up, are you ready to talk about GLBF?
Mute button. Yeah, maybe I can share the slides.
If you want, yeah,
if that's fine.
actually that might work better. Yeah, let me let you share the slides. That way, if I have to duck out of here, you're still in control.
Right. Just not sure.
Okay. I think you might have, if I'm looking at what's here, it looks like you asked to share the preloaded slides. So you'll have to get them out of the materials.
Yeah.
You want to instead share your screen, that's a different button on Meet Echo.
Right. I did that. I did slides requested. So if you can approve on that, is that?
Oh, I see. Hang on a minute. Go.
There
Luck
we
that
go.
worked.
Well, so latency GLBF, share.
Bingo.
All right.
Oh, wonderful that worked. Go for it.
Okay. So So these slides also say where they are on GitHub. Yep. Let's get directly to it as we don't have that much time. So just to be clear about how we think this to be positioned, right? So from our perspective, our main goal of what to get first deployed is still, what we've been showing in prior meetings, TCQF, QCF, because that has been validated in high speed implemented. So we have a much safer understanding about this. So GLBF is, from our perspective, a proposed second generation solution. It's incremental and integrative, so it keeps the benefits of the prior solution, and it adds the benefit of TSN ATS, right? So, and the gaps why we think it might take longer to adopt is that it depends on new header fields, right? So, which getting new packet headers in the IETF is always a big pain. We don't have any high-speed implementation validation, right? So the time frame in which that high-speed implementations might be feasible is an interesting question. And then also there has, of course, due to the recent time that this has been researched and developed, no formally independently validated calculus. So this is basically coming out of more explorative research, which we call latency-based forwarding, which I have the references to as well at the end and in the draft. So that was exploring what we can do with the packet headers, signaling the latency goals in the packet, minimum, maximum, and then doing the queuing for that. And that's all very cool and great stuff, except that it was so flexible that we couldn't figure out so far any calculus for the bounded latency. So that's when we went back and looked at the calculus that are available, and that's exactly the TSN-ATS calculus coming from the urgency-based scheduling research paper. And so ultimately we reused the damper mechanism from 30 years ago, even though we didn't know it by that name, and specifically with that TSN-ATS approach. And the use cases, of course, large-scale networks are not necessarily limited to that. It can also equally work well in small-scale networks, but cloud PLC, remote driving, machine robot control, outsourcing to the cloud of mobile device computes when you don't have the compute power locally. And ultimately, I think the industry is starting to develop this as control as a service. So I think overall, there might be, for all the large-scale networks that application we're thinking of, even additional chapters to, a BIS version of our use case document, but that's another story. Okay, let's understand the basic behavior of dampers and the problem statement, right? So we have two routers in a row. Router 1, we have some queuing scheduling, and we can calculate the bounded latency for that. So we're happy to provide a deterministic latency service. Unfortunately, when we don't do something specific, we will not be able to do that anymore on the second hop, because we have what we call burst collision, multiple flows occurring on router 1. They're getting delayed in router 1, and when they're then being rescheduled in router 2, we will have longer latency than we expect. This problem adds up across multiple hops, and so that's basically why we're starting to have all these convoluted algorithms we're talking about, because we can't, in linear fashion calculate the latency and guarantee it without them. And here is the simple, hopefully, visually appealing way to show this. So we have one green flow that we're interested in. It regularly sends a burst of 3 packets. And then on each of the other 3 interfaces, we have simultaneously occurring one, competing blue packet. So at the point in time where I'm showing here with hopefully my mouse pointer, you can see we have 4 packets in parallel. And when we look at how that shows up on the outgoing interface, then for the poor lack of loss, the 3 blue packets got in the outgoing interface queue first, and then come the 3 green packets from the green flow that we're interested in. And if we now look at it, then the 2 bursts of the green flow are closer together, and effectively that flow maximum burst has now doubled, and that is something we couldn't have predicted in our latency calculus. So on the next hop, we will have more buffer use, more latency for that flow, and we will have lost, our guarantee on the bounded latency. So now let's quickly revisit the algebra for the calculus, right? So the most simple method in which we describe the flow behavior is a rate in bits per second. And then the burst of a flow is given in the total number of bits. And the condition is that, the total rate of a flow can, over any period of time, not be larger than the rate and 1 burst. And then when you have these very simple description of flows in the way that UBS does it, we're ending up with a very simple calculus for the per hop bounded latency calculation, which is simply the aggregate of the bursts of all the flows divided by the serving rate of the outgoing interface, right? So you're not interested in the rates anymore that the flows have. They need to be admitted, so the outgoing interface, of course, needs to be larger. But for all intent and purpose, we are only looking at the sum of the bursts of the flows divided by the outgoing interface rate as the determining factor for the latency in queuing on that hop. And so the classical solutions, TSN-ATS, are solving the problem by when they do receive on the second router, doing that per flow shaping, or as it now called, interleaved regulator. And on the bottom, we're seeing the impact of this. So we're having here in red the 3 packets that we already saw in the prior slide. They're getting delayed because of competing traffic. And then the further blocks of the same flow are also getting delayed. But now it is because of the per flow shaper on router number 2 that they're getting delayed. And that way we see, visually nicely that the flow is never exceeding its maximum burst rate. And let's assume here at some point in time, the flow sets up to not send the burst. At that point in time, the per flow shaper, is going down again. And so afterwards, we would have the per flow shaper induced delay not anymore in the flow. So that's number 5 on the bottom. Okay, so, and then we have all these problems with these per flow shapers, right? So the provisioning issues that all the state needs to be pushed, which violates large-scale PPE design paradigms, creates churn on the control plane, and we cannot use source routing, which we like to use in large-scale networks like segment routing in the IETF, because we have the per hop per flow cross-packet processing. And then also what I mentioned already today and before, the read-write cycles of this shaper state, right? And this actually are the problems of the interleaved regulators of TSN ATS. Our good old RFC 2212 from the mid-90s is even worse. The inserv, there's also the overhead of maximum number of flows that we need to schedule. So here is basically, what I like to show as how we like large-scale service provider networks to look. We have the ingress and egress, so-called provider edge routers. We have the core routers, and then we have our controller plane up there. And when we use TSN ATS, we have all this signaling that needs to go between the controller plane and every hop for every flow, which is exactly this per flow state table that needs to be updated every time a new flow in TSN ATS comes along. And then, of course, when packets go through it, in this flow table on every hop, state needs to be updated at line rate speed. So we don't like that. And it doesn't scale. What we would like to have is exactly this model, where we have completely per flow stateless forwarding behavior in our bounded latency mechanism on all the core routers, and the only communication during the operation of the network that the controller plane should have is on the ingress router, on the edge, setting up the flows and making sure that when the sender is not complying to what was admitted, that those excess packets aren't allowed in. And so this ingress behavior, I listed all these different things that we can accept in here, and I think that goes a little bit beyond the core topic today, so I'm not going to discuss all the points here. So dampers, how are we getting rid of the per hop per flow state? We're pretty much considering that we do have the calculus in the first hop router that gives us a maximum limit for the queuing and scheduling. And actually, we also need to include the transmission over the interface to the next router. So we have the calculus to do that. We are taking a timestamp before the queuing router R1. That's the red T1. We're remembering that time. And once the packet leaves the queuing and scheduling, we're inserting into the packet metadata a target time T, which is T1 plus that maximum that we know from our calculus. So then the packet arrives at router 2, which obviously is at any point in time T1 equal or earlier to T1 plus max. So in our router 2, we take time number T2, and then we delay the packet by T minus T2. And that actually means that at this white dot, where we don't need to actually measure, it's just kind of a point of reference, that will exactly be the clock time T1 plus max. And at that point in time, we have reestablished the same sequence in time of the packets of all the flows that we had in router R1. So by that mean, we can apply exactly the same calculus for the scheduling again and don't need per flow state maintenance. So that's the basic dampers. And the interesting difference now, if we look over to TSN ATS, is that in TSN ATS, we only need to delay the packets when necessary, right? So during bursts and as needed afterwards. But when there is no competing traffic, packets will be delivered much earlier than the maximum latency for the hop, right? With the dampers, packets will always be delivered hop by hop with their maximum guaranteed latency. So isn't it better to deliver them as fast as possible, right? And the point GLBF makes, and I think a lot of other algorithms coming from synchronous delivery, is that this is actually beneficial to deliver them exactly in their guaranteed latency for synchronous delivery, control loops, and media playout. And it eliminates also the playout buffers, right? And it eliminates the need for clocks. And you can never guarantee the shorter latency anyhow, right? So it's very questionable how many applications actually do benefit from random fast arrival that is not guaranteed, which is what TSN ATS and other similar algorithms are offering. So here is the kind of picture I already showed some time back, comparing in typical control loop applications where you have one central element on the bottom called the programmable logic controller. Then you may have this, remotely driven car, let's say. The PLC is in the cloud, the sensors and actors are in the car. And so all these sensors and actors don't need to have their own clock and synchronization of that if the delivery of the packets is, as we call it, in time synchronous at their maximum latency, because the PLC itself can exactly know when packets arrive and when reply packets that are sent are returned when they have been sent, right? So because the latency through the network is known and it is always the same for every packet, independent of competing traffic. And if we replace that with TSN ATS, for example, then on the right-hand side, we have all these, wonderfully red circled additional components that we need to put into the solution, especially in very low-cost sensors and actors, which is PTP clock synchronization based on a local clock, playout buffers, resynchronization, right? So that is the added cost to applications if we do something like TSN with the so-called in-time delivery, in-time delivery where the packets may arrive earlier as opposed to synchronous on-time delivery, which is what GLBF offers. So let's look at GLBF now. The first thing to fix up versus the basic concept that we did was that the GLBF, as described in the first slide, still requires clock synchronization, and we really don't like clock synchronization in high-speed, wide-scale area networks. It's great. It does give potentially other benefits, but ideally, we should always have the option to not require it when not needed. And we can actually do this with GLBF because we can slightly fix up the algorithm, and that algorithm fix-up is shown here. So after the queuing and scheduling, we actually measure the time on R1, the sender as well. So we now know the total time spent in queuing and scheduling on R1. So we simply need to take the delta of that, subtract that from the maximum that we know. And so that is the missing delay latency that we know the packet now needs to experience. So we're not sending an absolute clock timestamp from router R1 as metadata to router R2, but we're sending the desired delay that we want router 2 to apply. So router 2 basically gets that and takes its local timestamp from a local non-synchronized clock and applies the latency. This needs to be T2 plus D, right? So it basically simply delays based on its local clock, and then we again get the equivalent of T1 on router 1 plus the maximum. Now, the calculation error that is shown here in red, that is exactly what needs to be thought of, and the most important part of that is actually simply the serialization latency, and that actually can be, captured by calculation on wired networks, and that's exactly what we're doing, and that's showing in further slides in the details, right? So this here is now adding all the actual stages of interest. So the main issue that was missing on the prior one is that serialization, right? So if you have a large network, obviously that does incur by pure speed of having to serialize 1500 bytes as opposed in a small packet 50 bytes, a higher latency to router 2, but obviously we can take that into the calculation. And so here are the updated calculations here. We're simply needing to introduce in wide a T reference, which is, let's say, the first bit of the packet when it is being serialized out on the link. We're not interested here to compensate for speed of light. So however long the link is, we're not interested in, right? So we just need to consider these routers are back to back. We're interested in TREF as the time when the first bit of the packet is seen on that minimum shortest link between router R1 and R2. We can calculate that from the measured time T3 on router 1, and then we take the packet size in bits and divide it by the serialization speed. Obviously, if there is sub rating on the outgoing interface, then you adjust that, right? So in any case, TREF can perfectly be calculated, and router R1 can calculate now the desired delay on router 2 by taking all that into account, right? Which is the maximum from the calculus, which is the maximum latency through the queue, the latency of the largest possible packet over the link, and basically from that, subtract for the actual packet the reference time, and then the T1 time that was measured before the queuing. So equally, when the packet arrives on router 2, the router 2 also needs to take the packet size and the serialization speed of the link into account to recalculate T reference, and then basically the delay is that T reference plus the delay in the packet, right? So this way we have what we call asynchronous dampers, and that's one of the first things of GLBF, kind of the core thing to make it work without clock synchronization in wired networks. So if we do have, for example, radio links where the propagation over the internet, over the interface, over the link, can be highly variable because of physical or link layer retransmission, or also reflections, right? So and those errors account to something we're worried about. Then on that link, we can simply use GLBF with synchronous transmission. At that point in time, we just need to have for that link, instead of a relative delay, we need to put the absolute timestamp in there, and the receiver needs to know that, right? So we could apply this to radio link, but I think that's a raw problem, so we can get to that later when we get to raw issues. But for wireline, there is no such issues, so the asynchronous model will work perfectly. So great, are we done? Yeah, it's great, but we're not done, right? So this is not good enough for standardization, and this is not complete enough for high-speed implementation. So let's see what we're missing here. So the first thing is that we were just looking into the arbitrary, somebody knows some form of calculus, queuing and scheduling of the packets. But if we're starting to say, hey, every vendor could do their own queuing and scheduling, we just need to add the dampers, then we can't build a standards vendor independent controller plane, because the controller plane needs to do complex calculation that take path selection and latency control into account. And it can't do that if for every hop it has some proprietary latency calculus, right? So we do need to select, in conjunction with a damper, a particular standardized queuing and scheduling mechanism with a published standard calculus, so that we can build a standardized controller plane independent of vendors. And so that's why in GLBF we chose to use the TSN ATS calculus, which is not only well known, published, well, mathematically proven, but it's also gotten good experience from TSN ATS. And we have the added benefit that we can very likely reuse almost everything from a TSN ATS controller plane as far as calculation of latency, path selection, all these things are considered. And so GLBF could become a plug-in replacement in the network for such an existing or shared controller plane implementation for TSN ATS. So now this is how GLBF completely looks. So this is kind of, as far as the model is concerned, the last slide on GLBF. And as we see here, we have replaced the one single block of queuing and scheduling with the queuing scheduling block of TSN ATS, which is a set of up to, I think, 8 FIFO queues, followed by strict priority queuing. And then you can easily understand from what I said in before that the latency of a particular flow through the router here is determined by the total maximum number of bytes, which is the sum of the bursts of the flows that are admitted in the prior one FIFO. And when we go to priority 2, it's the sum of FIFO 1 and FIFO 2 and so on, right? So there is a very clear and simple calculus to calculate the maximum bounded latency, and that is simply the sum of the length of the FIFOs of the priority of the packet and plus the lower priorities. And so then basically here the calculations are again the same as we did in before, because they're not impacted, but now we also know the calculus of the latency calculation for the controller plane. And we also know that we want to have in the packet metadata some additional way to signaling the priority of the packet, which could be end-to-end, so that the packet has the priority on every hop, the same. Or we would use a mechanism like, for example, we already showed in CSQF that we have per hop a different priority, for example, captured by the per hop sits that we use to steer the packet. And then the state in the router is we simply need to have the 8 maximum numbers that we pre-populate from the controller plane. So for each of the priorities, we need the maximum value so that we can do the per packet calculation to insert then the packet delay when we send out the packet, right? So this is, everything in one slide, probably too busy to understand the first time around, but slides are uploaded, right? So it's simply 8 values that need to be populated for the outgoing interface. The maximum bounded latency pre-calculated for each of the 8 priorities. And then these yellow boxes are the calculations that need to be done on the packet. And we think that with a very high speed, in-cache calculation and 8 variables that are always in cache, which are the 8 priorities, this can perfectly be done at high speed. So, but there is an issue with high-speed implementation, and so that is also now very much following the ideas that were explained in the UBS research paper for TSN ATS in terms of implementation. And that is, if you look at the point between the dampening and the scheduling, you can at that point in time have many packets. Remember the original picture that we had, right? So all these packets that are colliding at the same point in time, these would have to be, forwarded in exactly 0 time between damper and queuing. Otherwise, we would add delay in implementation, which we would need to be able to calculate, and it's very difficult, right? So the rule of thumb is you don't want to have a multi-stage queuing, one in the dampening and one in the following priority queuing. You want to bring that together into single stage, and that's the interesting challenge. And in TSN ATS, that was described how that is done. And so the interesting challenge was how to do that in GLBF. So the first likely ideal long-term implementation is to use so-called PIFOs, which are push in first out, but we're also calling it timed PIFOs. So PIFOs are ones where you're saying that the order of the packets in the PIFO are determined by their rank, and we use as the rank the target sending time, which is the time that that is being calculated for the damper. And then basically, when these packets are ready, we're using strict priority dequeuing timed, in terms of we're removing the packets only after they have met their target time. And so this is something which isn't entirely clear how fast it can be built. So I've been tracking what research has been doing on implementations, and they have actually gotten to the point where this year we'll see, I think, the first really good high-speed FPGA implementation of PIFO that scales better than the number of flows people expect to have in there. So the prior implementations weren't very good, but that still hasn't gotten to the point where we can actually clock timestamps as the rank of the PIFO. So there is still a little bit left to be done. I'm very positive that this can happen easily in the next few years. Yeah, so this is what I was talking about here in terms of, you know, the state of research and prototype implementations. And I'll need to start discussing the gaps that still exist on the research side for this option. So here is an option that can be built today, and as we'll see, that comes with an interesting twist. So this actually follows very much the high-speed implementation of TSN-ATS. And so what we're doing here is, instead of using PIFOs, we are using FIFOs, so that we can ensure that whenever we're enqueuing packets in one of the FIFOs, the packets need to come out in the same order. So we don't need to do that complex insertion sort that troubles PIFO implementation, makes them complex and expensive, and the subject of good research and what we're getting to. And so in TSN-ATS, exactly the same thing was done. In TSN-ATS, we have FIFOs based on per interface and per priority, so that exactly they can achieve the same thing, except that in TSN-ATS, packets are dequeued based on the per flow shaper, interleaved regulator, and we're simply dequeuing them based on the time, so we don't have that per flow state anymore. But what we need to do here is to make sure that packets are always in order. We need to have one FIFO per incoming interface, per prio, and per previous hop priority. So that's the P prio. That's so we basically need you know, some number of more queues, right? P prio times prio. So it's 64 times more, or yeah, 8 times more FIFOs than we would need in the TSN-ATS solution to do this, right? So so with that number of FIFOs and dequeuing based on that, this is you know, single stage, and it can be done today with a number of FIFOs. If we're looking at the number of FIFOs we already have in high-speed routers, so I'm not concerned of that being very well feasible. But the interesting challenge, of course, now is that we need to insert the packet based on the prior hop priority, so we need to be able to extract that from the packet header. So that's kind of, you know, we have a workaround implementation for the high-speed way, and we need to be able to still maintain that prior hop priority. It's not an issue in the SID case in SRv6. It's just a question if that's a good encoding to look that up, because you always maintain every hops sits in that. But if we come up with another header, then it might be another, you know, 3-bit field that we would need to have for this. So, and this is basically what I'm saying here. Validation. So we did do a simulation, an ad hoc simulation implementation for our research paper, and that was exactly replicating the minimum case in which we can show the problem of burst collisions. So we have 3 routers, each of them receiving 3 flows. So what we'll get is on each of the outgoing interfaces of router 1, 2, and 3, we will have packets where the flows bursts have become larger than they should be, but the latency through the router 1, 2, and 3, of course, is perfect, has been pre-calculated. But when these, flows now arrive into the router 4, then at that point in time, if we wouldn't do the in our implementation PIFO-based GLBF, but only a FIFO without the damper, then we will see that packets of the flows are exceeding their latency. Then to counter that argument, we enable GLBF, and we see that the latency is again within the pre-calculated bounds. And so this is exactly here the output results on router R4. On the top, you can see that there are some of these, black bars are the latency of some packets of the one flow we looked at, which are exceeding the pre-calculated limit of the calculus. And then we apply the dampers, and as you'll see, the packets are all perfectly staying on that router within the latency bounds. Yeah, so packet metadata encapsulation. So this is kind of for target, going further in the specification. So we've got the delay, the damper value for the asynchronous mode. If we want to implement synchronous mode, we would have the TD, which is a timestamp that could also be implemented in 20-bit resolution, because it could circle around synchronized in a 1 millisecond fashion. We do calculus math, so the timestamp doesn't need to be 128 bits or something like that. And then the 3-bit priority, and of course when we do the FIFO implementation, we would need to have the prior hop priority if that's needed, and then of course the sequence of priorities when we do that. So benefits summary, we're getting to the summary solution, right? So if we compare that with our current proposed first generation solution, TCQF, CSQF, we have somewhat lower cycle times, right? Because the cycle times is in the order of let's say 20 microsecond or larger, 10, 20 microsecond or larger. So we would be more accurate. How important is that? I think the main benefit can be asynchronous, right? We don't need any PTP clock synchronization. And we can also support jittery links, but at the cost of then having clock synchronization across the radio link, right? It is TCQF backward compatible, right? So we can set up TCQF we can set up GLBF to behave like TCQF. We simply need to make the buffers on each hop, the amount of admitted traffic that we do exactly the same size, and then we'll very much get into the same behavior as TCQF, right? Single priority buffer space exactly the same as the cycle buffer. We can likely make the same argument against CSQF. That would probably require more of a slide and picture work than I had time for this time to set this up with multiple priorities. So, but we do think that it is a nice evolution from first generation implementations with TCQF, CSQF, and then when the hardware for GLBF is available, evolve into this and gain the benefit of not having to do clock synchronization, and then the added benefits in terms of that we do have higher flexibility. We can have the buffer size on the different hops be different, and therefore potentially achieve more flexible admission control options. What's the benefit over TSN ATS, right? So obviously also backward compatible insofar as that it maintains the calculus of that solution. So as I already said, it could be a plug-in for the same controller plane. It is equally asynchronous, and we do have the on-time packet delivery. So we don't have the jitter of TSN ATS, something which, remember the slide with the control loop environments, something which makes applications more difficult. Okay, so overall, what's the takeaway? So GLBF is an adoption of the old damper ideas, enables per hop, per flow stateless operation required for large-scale networks, has minimal or no jitter, minimal or no playout buffer requirements, and the time for that seems to be right. It seems to be feasible to implement high speed with FIFO and PIFO options, but it doesn't exist today, so it will take somewhat longer than other options like what TCQF is. The specification contributes the per hop asynchronous and or synchronous operation, the use of the UBS calculus, the proposals for high-speed implementation, and then the combined benefits of TSN ATS and TSN CQF. So it's designed for large-scale networks, but it should likely also be very beneficial to smaller scale networks like the existing one, or even when people build it into low-cost, let's say in-car systems. Okay, our references, and that's it. Thank you very much.
Okay, comments, questions? Shinu, go ahead.
Thank you. Can you hear me? Oh, yeah. Thank you, Troas, for the wonderful and nice presentation. I really appreciate it. And I do agree to the basic idea of the dampening. Actually, the one of the idea that I have presented in the previous asynchronous deterministic network framework document has the similar idea. As I told you in the previous email, the basic difference between two, I think, is that you dampens every node, but in the buffered network that I have presented, buffers only once at the network boundary. I think both are feasible way of making jitter guarantee. But I wonder what kind of advantage you have when you're dampening in every node.
So right, so unfortunately I will have a picture of the topologies I'm always thinking of, because those are the ones that I work with, and those are rings in metropolitan area networks, and that means on every hop you have a lot of traffic that enters the ring, and that's exactly creating the hard to calculate latency. And you have large number of hops. You may in these rings have 20 or more hops in large scale environments, and so that's why I do think. See, it's hard to think of hardware that you can build and say, hey, this isn't doing the per hop dampening here, and it makes the box cheaper, and there is a guaranteed place where you can deploy it, right? So given how we start thinking of, okay, we're selling the boxes, it needs to be able to do the dampening anyhow. It's one kind of implementation fits all places. Then comes the question, okay, do I gain something by not enabling the feature on a particular hop? And I think it doesn't, because as soon as we dampen on a particular hop, we are again to the very simple calculus that we have, which is the latency is just the sum of the buffer sizes. And I do think it also therefore keeps it a minimum, right? So if we go back to the validation slide, right? So if I would keep, where is it here? Right? If I would keep through router 4, if I wouldn't do the dampening on router 4, now on the next hop, I would have to try to figure out what is the bloody calculus to capture the added latency that I have in this case, something like 2,800 instead of 2,200 microseconds for the worst case flow, right? Why would I get into the trouble of doing that? What's the benefit, right? I need to be able to have in the hardware the dampener everywhere. I don't expect that to be an added cost in forwarding packets, reducing the performance. So I don't see the benefit of not doing it. I only see problems occurring with it.
If I continue a little bit more, yeah, but you still need to have a forwarding function, such as ATS. in order to guarantee the latency?
I need to have the damper, the damper behavior that I showed, like the high speed FIFO or PIFO versions. Yes.
What I want to say is that you still have a forwarder or QQ with the damper, and the major part of what the latency is guaranteed is affected by the forwarder. So if you use just FIFO, the bound becomes very large. And if you have a more elaborated or sophisticated scheduler in front of the damper, then the worst latency will be much more smaller. So it will be a very good idea to have a nice scheduler or sophisticated scheduler in front of the damper, not just a strict priority queue. That's my comment. So my idea is to have a very high-speed network that serves the packet as soon as possible, and then just dampens at the network boundary. I think that is much more simple.
Yeah, but you know, I think so. I mean, we saw if we have the really important ring topologies for metropolitan areas, then we cannot calculate across multiple hops the bounded latency if we're not doing per hop, either interleaf regulators, ATS, or dampers, right, or cycles, right? Any of these per hop things to make the per hop latency easily calculated in our calculus, right? We don't have the math for that.
Yeah, well, we can have a better scheduler everywhere, like fair queuing or deficit round robin. Those can be a lot better than the FIFO-based scheduler. Why don't we use that?
So
Okay, let's see if we can get the last couple of questions in before the bottom of the hour. So I guess Charles, quick response, and then we'll go to Zhengdong.
no, I think let's continue that on the list, Jiandong. Thanks very much for the feedback. I think we need to continue that discuss.
Okay, Zhengdong, go ahead.
Thank you for your presentation, Natolis. I have a few clarification questions. Now, one of the question is, in one of the slides with the timing models, I think I heard the term serialization speed. Is this the same thing as link capacity? Or
It's
it's
link
different?
speed. So it's, let's say, 1 gigabit per second. So that's 1 gigabit per second is the serialization speed.
Oh, okay, same thing as link speed. Okay, thank you. Second question is on the second or third page from the back, you mentioned the CSQF. What is CSQF?
Oh, this is the proposal with the cycles, where which is similar to TCQF, but instead of doing the cycle mapping through a mapping table on the router, the cycle for every hop is indicated in the packet header, for example, through the segment routing header, where it comes easily.
Oh, you mean SCQF?
I thought it was
Segment routing.
CSQF, I think. Cycle-specific forwarding and queuing, CSQF. And I think I'm also guilty of having places where I misspelled it.
Oh, okay. Anyway, thank
Sorry
you.
about that. And the draft name also doesn't have the CSQF abbreviation in it. So sorry for that. Yeah.
So that draft is from Mark Chen and Sui-Song and right?
Yep. Yes, exactly.
Okay. Okay. Thank you.
I will have a comparison of those in the 117 presentation. Yep.
Okay, Alexander.
Okay, thank you.
mute button, Alex. There is the microphone icon that you need to click on.
Alexander, we can't hear you. Do you have another mute you need to clear? All right, Xiaofu, I think you may get the last word here, or close to it.
Okay, I just talk it quickly. Thomas, can you respond to my concerns in the mail list that I just sent it to you? I think this question is related with the question that Jinu just asked to you. Thanks.
Okay, well, we'll do.
Okay. And with
Iju
that,
is trying to get a last word in, if that's still.
Iju, go ahead. Will be nice.
Just unmute yourself.
Can you hear me?
Yes.
Okay. I have some actually clarification questions. So at your second bullet, you say you need a separate FIFO for each of the combination. So that means we need a combination for multiple FIFO queues and plus FIFO, or?
No. These are two alternative options, right? So the first option here is in the FIFO, we simply need one FIFO per priority, right? So that looks very nice and easy. So 8 FIFOs.
Yeah.
And then if we don't want to have FIFOs because we don't yet have the high-speed implementations, we need to have FIFOs, but we have one FIFO for the first incoming interface and the first priority and the first prior hop priority. Then we have another FIFO for the incoming interface 1, priority 2, prior hop priority, so on. So you have, if you have 8 priorities on every hop, it's 8 times 8 times the number of incoming interface. And this is exactly very similar to the way that TS and ATS FIFOs would work. You would have in TS and ATS, you have a FIFO for every incoming interface and every priority. So the new trick that we do for GLBF to make FIFOs work is to also factor the prior hop priority.
Okay. I see. And for the very last sentence, except no shaper state or processing. So when here says except no shaper state, do you mean we don't need the leaky bucket, the CBSCR?
No, exactly. The only thing that happens is that you have the strict priority dequeuing, and it looks at the rank of each packet, which is the pre-calculated TD, which is, the pre-calculation was in the other GLBF slide. So it picks the packet with the earliest TD that is already reached, right? So you are at some clock. So you have a local clock, and you're comparing the TD of the head of all the FIFOs, and the first TD that is now reached of the highest priority is the FIFO from which you're dequeuing the packet. So it's a simple parallel comparison of these, ranks, as we call in this land. And that's what's being dequeued. So that's proven to be very simple to implement in parallel in every FPGA. And I think it's a good point that you asked this. So I should, have redo a slide to show that detail in the slide itself.
Thanks. And the very last one, I see there are 2 points we need to do the measurement, which is behind the timeline T, and the other is behind the timeline T2.
Right.
I may miss some of the previous slides. So why we need a 2, especially for the later one after the T2? What are we measuring for here?
Oh yeah. So basically the thing that we need to. So first of all, measurement simply means you're having a locally free running clock and you're basically, in your forwarding engine, you're taking that clock value and doing the simple math with it, right? So the measurement is a little bit of a overwhelming term for taking the local clock value. And you need to take the local clock value at T for received packets, and then for forwarding it further out, you need to take number T2, right? The whole point, what you want to do is the difference between T and T2 is the time that the packet has actually spent. And you never know that because, the time that the packet spends because of competing traffic, that you cannot predict. And that is exactly what we need to measure, right? So that difference, that's why we need to, measure, remember when the packet passes the point T, the clock there, and then we subtract that at the point T2, and that way we know the time that the packet internally has spent, however many microseconds it has spent there, and that's basically then part of the calculation when the packet is being sent out.
So that's, sorry to jump in. So that's in order to avoid synchronization between neighboring nodes, right?
Yes.
Okay.
Okay.
Yes. But again,
this
I mean,
point,
you have
I need to.
Yeah, sorry.
So at this point, I need to leave, which may or may not close the meeting. I don't know whether the meeting is going to shut things down. Thank you very much, everybody. And Turles, thank you. You've generated useful and interesting discussion, which was the goal.
Yeah, so let's see what happens when David leaves. All doesn't seem to be killing it, but...
Turles, can I have one more last question, maybe? I have just make a note on the chat list.
Mm-hmm.
The reason you can build this with the FIFO based on priority is that you have the assumption that all the flows in the same priority get the same maximum latency per node.
The whole point, and that was explained in the UBS research paper, where, as I said, they do the very same scheme, is that you don't, when you receive packets, you can only put those packets into a single FIFO that will be removed in the same order in which they arrive, right? You don't want to have the problem that you receive a packet, you calculate when it gets out, and basically you need to insert it somewhere in the queue, in the middle of the queue, right? That's why you need PIFOs. So you can always replace a PIFO with a set of FIFOs when you do figure out, hey, wait a second, I can figure out the packet belongs to a subset of other packets that will be kept in order. So a new packet that arrives simply needs to be put at the end of that FIFO, and then I don't need to insert it somewhere in the middle. And so this is what we do with the scheme, and the only intelligence we need beyond that is that we need to dequeue it at a certain point in time, and that is exactly what we need to look at only into the head of each FIFO, right? So we only need to compare these pre-calculated times when these packets need to be dequeued.
Well, my question was very simple. Different flows may want to get different maximum latency per node. My question was, do they get separated for different maximum latency?
Yeah, so basically, this is the UBS calculus, right? So let's say we have up to 8 queues.
But I think that the UBS and the damper is not exactly the same. So
no, wait a second. But the latency calculus of GLBF is still the UBF calculus. So with respect to calculating the latency of a particular flow's packets, it solely depends which of the priority on that hop it gets into. So let's say each of the 8 priorities has a maximum buffer size of, let's say, 10 microseconds. Then a packet in priority 1, the highest priority, will have a bounded queuing latency through that hop of 10 microseconds. In priority queue, it will have a maximum latency of 20 microseconds, which is the latency of any priority 1 packet plus the latency of priority 2, right? So each is 10 microseconds. So every priority 1 packet will be served before priority 2. So 10 microsecond plus 10 microsecond makes 20 microseconds. Priority, same thing again, 10 plus 10 plus 10, 30 microseconds for priority 3. So that's a very simple UBS calculus. And exactly the same calculus is what GLBF gives you.
In the UVS, even the flows within the same priority can have different maximum latency because they are regulated by their own flow parameters. The flows have different parameters, so
they have different parameters, but they don't impact that doesn't impact the bounded latency guarantee on that hop. The bounded latency guarantee on the UBS hop is solely based on the priority queue length.
Well, do you have any mathematical proof?
Oh, that's the UBS research paper that started the whole TSN ATS work. Yeah, I think I should have that. Let me see that I have that reference in the draft.
Exactly the same. It is different. Okay, let's close the question today.
Yeah.
Thank you.
Yes, I just have the same question. I think the queuing delay and the shipping delay are different things. So according to damping function, each packet may have the same worst case latency per hop. That is my understanding.
In the GLBF, let's go back to that. As you see, the maximum latency through the hop is different based on the priority that the packet has on this hop. So if we use the UBS, so this is basically why we need in the packet header some metadata to indicate for this hop the priority, right? So packet comes in here, and in this box measure and dampen here, we will look up the priority. From the priority, we will look up the maximum value. And sorry, this actually happens here on the second block, right? So the measure and mark. In the measure and mark, we're basically looking up the priority packet.p here. Then we take the max1 value, which is the calculated maximum latency for that priority. And then basically we subtract that from that, the times that we've taken, and that is the damper value we're inserting.
Yes, my question is that for all packets belongs to the same priority, do we experience the same worst case latency per hop?
Yes.
For example, for the priority 1, the worst case latency per hop may be, for example, 10 microseconds. So all packets belong to the same priority 1. We experience the same delay per hop that is 10 microseconds.
Yes.
Okay.
And the interesting aspect, of course, is when you do have a flexible scheme where you can give a packet on each hop a different priority, you can very nicely fine-tune the end-to-end latency by, for example, saying, hey, I want to have something that's in between the end-to-end latency of priority 2 and 3. So you'll kind of, give the packet priority 2 on one hop, priority 3 on the next hop, priority 2, 3, 2, 3. So you're kind of dithering between per hop priorities to create end-to-end, fairly large number of different latency experiences when you want to. Okay, I think we ran out of questions. Thank you very much, everybody.
Okay, thank you. Bye-bye.
Bye-bye.
Thank you. See you in San Francisco.
Yep.
Bye.
Bye.